Hello, everyone. I'm Mingsheng, and I lead the engineering work on Google's TensorFlow runtime. Today, I'll be sharing some research and engineering problems in building ML infra, which I think the data infra and system communities might be able to help. This is based on a talk I gave at VRDB 2020. Big data and ML workflows tend to overlap and complement each other in accomplishing end users' tasks. For example, here we see a user journey from left to right in ingesting, processing, storing, and analyzing the data to derive intelligence. Along this journey, both data and ML infra play important roles, and they have a lot in common in the amount of data and computing resources that they consume. In terms of impact, data and ML infra have both become some of the key foundational technologies that power a lot of our business and personal needs. I have had the fortune to work on both kinds of infrastructure. I spent 5 years in database research as a grad student, and 10 years after that in working on various data infra products across 3 companies. I then joined TensorFlow about 3 years ago, attracted by Chris Latner's vision in framing ML infra as a compiler and runtime problem. Previously, I worked on SQL query optimizers and execution engines, which are special purpose compilers and runtimes. And I always wanted to learn more about the underlying principles and technologies in building general purpose compilers and runtimes, and see how they're related to the SQL infra I have grown to be familiar with. 3 years is not a lot of time, but in the still young and fast-moving field of ML infra, I was able to gain some new insights that have made this journey rewarding. And today, I would like to share some of the observations and interesting problems with you all. Let me first make a pitch on why you should care about this. First, for researchers and engineers, ML infra is a fascinating subject because it touches such a wide range of core computer science and double-E subjects, from hardware design and programmability to systems infra to programming language and compiler design, and also the co-design between ML and systems. I personally have been having an intellectual blast in working with some of the best minds and tackling cutting-edge problems. To give you an example, I was fortunate to get involved in a research project called Mesh TensorFlow about 2 years ago, where we built the programming abstractions and internals for running huge ML models. A core part of the technology is how we execute a giant matrix multiplication or matplotlib across a cluster of machines. Our design is similar to how you would run a distributed join. One version is that for the 2 sides of the matplotlib, we replicate one side and shard or partition the other side. That sounds familiar, right? Also, ML infra is still relatively new. TensorFlow was started in 2014, and one of its predecessors, Theano, started in 2007. There is still a lot of innovation and impact to be made. Here are some of the driving forces behind the rapid pace of the innovations and the adoption in the new ML infra. First, Moore's law is dead, and we're now in the era of domain-specific architecture, as Hennessy and Patterson proclaimed in their Turing Award lecture. But new hardwares don't run themselves. They require good software, especially in compiler and runtime, to maximize their impact. Next, the continuous innovations in ML modeling, far beyond the classical SGD or stochastic gradient descent, put more pressure on ML infra to evolve and fulfill their needs. Last but not least, new ML deployments are springing up almost every week and every month, ranging from data centers to your personal mobile devices and to IoT devices that are becoming more ubiquitous. ML ML infra has attracted a lot of R&D investments and innovations over the past 5 years or so, especially since the open sourcing of Google's TensorFlow. As a case study, TFRT is a new runtime being built at Google with community support. We're also hiring, by the way. If you enjoy this talk and you would like to learn more about this project and other opportunities in building cutting-edge ML infra, please feel free to reach out to me. This is a talk agenda. We will first introduce the general design of ML frameworks like TensorFlow and PyTorch, and contrast them with database query processing. We will then talk about some R&D problems in different layers of the system, from the top level of user API and language design to the middle end of optimization, and finally, a bottom layer of the execution. We will then wrap up this talk with some call to actions. So let's dive in. The heart of an ML program is often a data flow graph, where the nodes or operators and edges represent the data flow. Such a graph focuses on specifying what to do and not how to do it. Sounds familiar? Yes. The graph is mostly declarative, just like relational algebra in SQL. Before we execute such a graph, we will want to do various optimizations to improve the performance of the graph execution. Now, let's look at how to create such a graph. Here's how you do it in Keras, one of the popular ML APIs. Keras has multiple backends, with one of the most popular and most engineered backends being TensorFlow. Another popular API in the associated framework is PyTorch. Although the syntax looks somewhat different from Keras, they both focus on building data flow graphs that I showed you earlier. As you can see, popular ML APIs tend to be using Python as a host language, given its flexibility and extensive community support in scientific computing libraries like NumPy. The actual heavy lifting of the computation is often done in C and C++ components, but Python is a nice glue language that calls into the C layer. Unlike SQL, for data processing, there is currently no standards of ML APIs or languages. But for the purpose of this talk, you need not care much about the syntax. Now, let me tell you about how an ML program gets optimized and executed. If you know about SQL query processing, I think I can describe the ML infra architecture to you in 3 sentences, and you will be able to understand it reasonably well, even if you have never looked into the inner workings of the TensorFlows and PyTorches. Shall we give it a try? First, user writes a program against the APIs that I just showed you, and the API calls result in a high-level data flow graph. Next, the graph compiler would optimize and compile a high-level data flow graph down to a low-level execution graph, similar to how we would create a physical query plan from a logical query plan. Finally, the runtime executes a low-level graph by dispatching what's known as kernels in the graph, analogous to physical operators, and run them on the associated devices. That's it. Congratulations. In 3 sentences, you have now understood how ML infra works, and maybe this is a sign that you could also try working on it. What kind of graph optimization is possible? Here, we see a part of a real ML model running in Google's production. This model does independent scalar normalization across 18 floats. For normalization, you can think of this applying some scalar transformation, like subtracting a constant and dividing by another constant. And then concatenates the 18 normalized scalars into a one-dimensional tensor, also known as a vector. We implemented a graph rewrite path to vectorize such scalar ops for normalization. The idea is to first concatenate the 18 input scalars into a vector, and then apply the same normalization over that vector. And this led to a huge reduction in the number of ops we need to dispatch to execute this model. And that in turn led to a big win in both latency and CPU cost. To be clear, what we have just covered is a workflow referred to as graph execution. And there's also a workflow of eager or op-by-op execution, which dispatches the individual user API calls directly to the runtime, without having to create and optimize a data flow graph first. While eager execution might deliver lower performance than graph execution for some workloads, in exchange, it tends to provide better usability and flexibility. For example, since user API calls get processed at the runtime right away, when errors happen, they can get propagated back to the end users immediately, often with a more accurate error context. TensorFlow will continue to support both eager and graph execution. In this talk, though, we will focus on graph execution, since that's where we have most of the optimization opportunities. By now, you have seen that both data and ML infra deal with a set of operators with algebraic properties that can be used for graph optimization. The SQL query plans and ML computational graphs both have data flow semantics. That means there is no program counter, but instead, a downstream node in the graph gets activated when all its upstream dependencies have been computed. To scale up this data processing, both kinds of infra employ all kinds of concurrent and parallel mechanisms. For example, TensorFlow supports both inter-op and intra-op parallelisms. Inter-op parallelism allows you to concurrently execute a set of nodes in a graph. Intra-op parallelism allows you to run a single op either over a CPU thread pool, or on a local machine, or on a set of locally attached accelerators like GPUs. For a truly gigantic op, like a giant macro, it is also possible to run it across a set of machines, as in the mesh TensorFlow work I described earlier. Both kinds of infra tend to run on large-scale clusters, and they tend to fulfill cloud computing types of requirements, like being elastic and fault-tolerant. Of course, there are also some key differences, and let's look at a few of them. First, while relational or tabular data is important for ML, other forms of data, such as text, image, audio, and video, also play a critical role. Interestingly, image data could capture other forms of data that may not be thought of as images, such as chessboard positions and spectrograms of sounds. And this increases the expressive power and the applicability of image-based ML models. Here we show one example where the ML model can tell apart the sound of a gunshot from a call horn based on the sound spectrograms. And that's pretty cool. Next, the data infra community is really good at optimizing I/O by exploiting the access patterns. For example, to speed up lookup queries, we can create irrelevant indices. Unfortunately, the access patterns in ML training are some of the worst from data infra optimization point of view. They often consist of full table scans combined with randomized shuffling. And this is to help make sure the trained ML model is not overfit to the particular ordering of the training records being fed into the model. So there are good reasons. When we repeatedly feed the training data set into the model, we would shuffle the input records. But this makes it really challenging to pre-process the input by constructing indices and materialized views. Another difference is that an ML model, ML program, might contain control flow, such as a conditional branch or a loop. And this is different from classical relational algebra or SQL, which is not as expressive unless you use the SQL with clause or resort to user-defined functions. While SQL is Turing complete, the mainstream workloads that involve select from where, group by, order by, do not involve control flows. So how do we handle control flow in ML infra? There are a few design options with their own trade-offs. First, we can break up the ML program into multiple graphs separated by the program control flow so that we need not support in-graph control flows. But the scope of each optimization call will now be limited to each individual graphs. So it is less likely you can do cross-graph and holistic global program optimization. Next, we can add control flows into the graph like TensorFlow does. But this introduces non-trivial complexity to both the compiler and the runtime infra. We can also try generating a data flow graph after evaluating the control flow. In this example, say we know B is greater than A. We can then create a graph at runtime by adding tf.add and tf.value into a single data flow graph. This approach sounds nice when it works, but if the values of B or A depends on the prior evaluation in the graph, then this technique would not work. For example, say the if condition compares Y with A. Then we cannot defer the computation of Y till after we have evaluated the if condition. Another concern is that this could lead to too many different variants of the data flow graphs, depending on which control flow branches are being taken at runtime. So graph compiler, I have to spend non-trivial time re-optimizing some of the subgraphs. As you can see, building ML infra can be highly non-trivial, and it provides good job security. To facilitate the collaboration between the data and ML infra communities, it will be useful to first get aligned on the terminology. So here we created this Rosetta Stone. The data flow graph we just talked about corresponds to a SQL query plan. And op is a specification of a computational unit and can be composed with other ops. This would correspond to an operator in a logical query plan or in relational algebra, such as a join. A kernel is a concrete implementation of an op and maps to a physical operator like a hash join. In ML infra, an op is often supported on multiple devices like CPUs and GPUs through different kernels. When we compile a data flow graph for execution, we are mapping the ops to the relevant kernels. And speaking of graph compiler or optimizer, we call it a query optimizer in data infra. A graph optimizer takes and returns graphs. How do we represent such a graph? In ML infra, as well as compiler literature, we use an intermediate representation or IR. It's basically a computer language that's designed for machine processing and not user-facing. For SQL query optimization, we also have such an implicit language, but often it's just a bunch of in-memory data structures like DB2's query graph model. For the compiled graph that's ready for execution, ML infra does not yet have a standard term, so we can call it a binary or an execution graph. In SQL, we would call it a physical query plan. Finally, we have a graph executor runtime, which corresponds to a SQL execution engine. Having covered the background, now let's look at some interesting problems. And this is a reminder of the three-layer architecture that we will go through. We will start top-down, from the user API to optimization, and finally execution. First, the tensor algebra consists of a set of ops that take and return tensors. A tensor is just an n-dimensional array. I put a quote on algebra since this is not yet a standard term in the ML infra community. Some example ops include matmul for matrix multiplication and tensor addition. These ops are declarative, as they do not specify how they are implemented or on which devices they will run. As you can imagine, the implementation of the same matmul op can be very different between CPU and GPU. But when model builders write their ML models by adding the ops to the models, they don't need to understand how the ops work. Also, just like SQL databases, ML infra supports user-defined ops. So that's the basic setup. It's not too different from SQL so far, right? Now, let's look at some interesting problems. First, there's a bit of a difference in the number of ops we're dealing with. SQL optimization has a large focus on 5 operator types. You have the filter, projection, join, group by, and order by. Of course, that's an oversimplification. There's also SQL 99 analytics and other advanced features as well. In contrast, TensorFlow has just a little bit more operators, around 1,500 of them, ranging from the common ML and numerical core capabilities like matmul and convolution, all the way to the more mundane tasks like reading files and printing tensors. Some people say that TensorFlow is like an operating system or Java Enterprise Edition, and that's not always a compliment. Second, researchers are looking to build ML models that work on not just rectangular tensors, but more advanced data types like trees. This is a bit like user-defined types in SQL, and it adds more complexity. Overall, it is still debatable how declarative a programming model could or should really be, given a host language is something really powerful and flexible like Python. That's not always the case, but Python for now is still the mainstream user-facing language. Now, it feels to me that over the time, people are converging on using a subset of the Python language that is friendly for optimization by the ML infra. So to summarize, I would expect there will continue to be a tug of war between the expressiveness and the performance considerations of the ML models that people will build. Now, let's talk about a really exciting subfield in ML infra. It's called input pipelines, and that's similar to the ETL pipelines in data infra. ETL stands for extract, transform, and load. The input pipelines is an important component in ML infra, and it's responsible for feeding data continuously into the model training. The training often runs on special purpose accelerators like GPUs and Google's TPUs. These accelerators are hungry beasts, and to avoid starving them, we need high-level, high-performance, and large-scale input pipelines to read, transform, and backtrack the data. Input pipelines often have their own API design and optimization opportunities. Here, we see 2 examples with different API styles. On the left, we have an example from TF data, where we can train up a set of API calls to construct an input pipeline in what's called a fluent API style. This is where, in this example, we take a data set, a data source from DS counter, and let's say for every 10 elements that we read from the data source, we batch them up and produce a single output record. We will do this for 10 times. And if we run out of input records, we're going to ask the input data source to repeat from the beginning. So that's what this example means. On the right, we have another API design from Fast AI, one of the popular machine learning API libraries, where we're reading a bunch of image files. For each image item, we will resize it to an image size of 224 pixels. And the rest of the options here are not worth discussing. Now, let's contrast these API designs with Spark. And you will find the designs are pretty similar, especially with TF data. They both have the fluent API style, where you chain up the API calls. And the similarity does not just stop at the API syntax. Similar to SQL and Spark, these input pipeline APIs express what to compute and not how. As such, the ordering of the API calls need not dictate the ordering of the execution. Instead, an optimizer can figure out how to run the entire program in an efficient and scalable way. For example, if you run a very cheap wrap function on each input record, and then you batch up the records, the optimizer could decide to first batch up the input and then run a map function in a vectorized way to amortize the cost of the function invocation. And this is similar to the vectorized normalization that we saw earlier. So these input pipelines would be awesome for SQL-style optimizations, right? If we ever apply extensive map functions like JPEG image processing, then we could even pre-process the data set and materialize the results before the ML training even starts. These kind of optimization ideas indeed can be applicable in some cases. But ML researchers also found that by randomizing the input on the fly of the training, it could make the training even more effective. This is similar to teaching a kid to recognize a teddy bear. If they have seen only a single text image, their idea of a teddy bear might be somewhat limiting. But if you show them the same teddy bear from different angles and sometimes cropping parts of the image, and you still tell them that's a teddy bear, then it could enhance their understanding. Similarly, input pipelines have been extended to support such randomization on the input, also known as augmentations. When such augmentations are applied, we cannot fully materialize all possible augmentations, but we can still try and find some sweet spots between what we pre-process, what we compute on the fly of the training, and also what is the amount of randomization needed to get good enough training results. And there can be opportunities for systems infra and ML co-design. Now, let's talk about optimization. All of you are pretty familiar with the general query optimizations based on rewrite rules. This applies to data flow graphs for ML programs as well. For example, if we add the same tensor in times, we can just replace that with a multiplication. Here, we have some interesting optimization problems. First, recall that an ML framework like TensorFlow has thousands of operators, with new ones being continuously added. While it is possible to keep extending the graph compiler to optimize for newly added ops, this could add non-trivial engineering work. One option is to teach the optimizer to walk over operators based on their properties, not their names or identities. This way, the hope is that a single rewrite rule could apply to all operators that fulfill certain properties. But we still need to do some research to flesh out this set of properties. Next, sometimes the graph compiler only has limited information to work with. For example, each tensor has a few important properties or metadata fields. When we have a floating point matrix with dimension 2.2 by 3, and we say that tensor has a data type of D type of float 32, a rank of 2. Rank is the number of dimensions, and a shape of 2 by 3. When the graph compiler knows about the rank and shape of the tensors it's dealing with, it can do more effective optimizations, like allocating the right amount of memory, and also deciding which kernels to dispatch based on the input size. One possibility is to defer some of these optimization decisions to runtime when we actually know about the information. Since the execution graph is itself expressive enough, it should also be possible for the optimizer to generate code which will make the relevant optimization decisions, such as kernel selection, at runtime. And this is an area that's not much explored yet. Finally, is it possible to build a unified graph optimizer across a set of ML frameworks? After all, they all want mostly the same thing, like map modes and convolutions, just with different APIs. Could we end up building a single compiler in runtime that uses them all? That would be interesting to explore. Now that we have talked about rewrite rules, we should of course also talk about cost-based optimizations. This is very popular in the data infra community, but it's still relatively underdeveloped for ML infra. I can tell you though, there are a few possible use cases to motivate such work for ML infra. First, when we have multiple CPU ops that are ready to run, if some of them are small enough so that they can together keep all the CPU cores busy, then we should run them concurrently. But if we have a single large mode, that maybe we should run it to completion first and let it consume all of the CPU cores. And this way, we can get the best cache efficiency, and deciding between these options would require a cost model. Second, similarly, if we know that op is expensive, we will want to dispatch it to a thread pool so that the caller thread does not get blocked, and you can process the expensive op across the CPU cores in parallel. But if it's cheap, then it will be better to run it inline within the caller thread to avoid the thread pool dispatch and asynchrony overhead. Finally, the input pipelines should run somewhat ahead of the model computation via a form of prefetch. And this needs some tuning. If we prefetch too much, it could cause CPU contention with the actual model computation. But if we don't prefetch enough, it could slow model computation. So prefetch tuning could also use a good cost model. Another interesting area of optimization is to propagate selected data properties along the data flow graph. For example, a batch of images is often modeled as a four-dimensional tensor, with the batch dimension denoted as n, the image height, and then the width w, and the channel c. When we process these image batches on GPU and CPU kernels, the kernels can be optimized for specific input tensor layouts, like putting the channel dimension as the second dimension or the last dimension of the tensor. You can think of this as being analogous to choosing columnar table layouts versus row-oriented layouts in data infra. The problem statement is that given a graph of ops, how do we select the kernels and how do we pick the layouts to minimize the cost of layout transformations that have to happen at the runtime? For example, if a downstream kernel wants to consume the input in NCHW format, we can then try and propagate that preference upstream and see if upstream kernels can already produce the output tensors in that desired format. This is analogous to SQL query optimizations based on physical properties like the sort order or the segmentation of an input and intermediate table. Now, let's look at execution. First, I/O optimizations remain critical, since accelerators' peak performance appear to be growing at a faster rate than the advancement of I/O hardware. To avoid having CPU-based data preprocessing become a bottleneck for model training over GPUs and TPUs, one direction is to move the data preprocessing onto the accelerators whenever possible. Now, this introduces strong coupling between input pipeline and model computation. Another idea, which goes almost in an opposite direction, is to further decouple them by offloading input pipelines to remote workers. And that is consistent with the general trend of disaggregating hardware in cloud computing. As of now, it's not clear which camp will win, or maybe we will still be both. And this reminds me of my time at Vertica, where based on the original C-store design, there was a strong coupling between the storage and querying layers. For example, Query Optimizer would understand how a particular table is segmented across the cluster, thereby avoiding the I/O shuffling when possible, when it tries to optimize a distributed join or a group by. But then we have new data infra systems like Hive and Cloudera and Kala, and initially, and they just focus on scaling data from a distributed storage layer like HDFS. And some of the folks initially thought, some of the folks at Vertica saw that this will never fly. It will be just too slow. It won't be scalable. But over time, people recognize the benefits of having such a loosely coupled system, especially with data lakes being an increasingly more common part of the data infra in the enterprise. And eventually, Vertica also made an extension that made it possible to decouple storage from query. It's called EM mode. The classical SQL query design uses a pool-based iterator model with the use of exchange operator for parallelism. This design is known to achieve simplicity, such as managing the state as part of a join or a group by processing. For example, to implement a simple hash join, you can usually start by pooling or consuming a small side of the input, and then build a hash table, and then you start pulling a large side of the input to probe the hash table. And a more sophisticated implementation can involve handling splitting of the hash table if it's too large. If you implement the same algorithm in a pool-based engine, it will be quite awkward and complex. In contrast, ML infra, such as TensorFlow's runtime, does not do set-oriented processing like SQL. Instead, one record or one tensor flows through the entire system at a time. And as we discussed earlier, downstream nodes in the dataflow graph get activated when the relevant upstream computation is done. And so this is a push-based model. In the new TensorFlow runtime TFRT, by using a mixture of the push-based execution model and the use of futures, we have managed to make the runtime never block any compute threads. And this is a useful property to make sure CPU cores are used efficiently. It is not yet clear to us how this can be achieved in a pool-based execution model, and this will be an interesting topic to explore more. For distributed and parallel execution, there has been two different paradigms. The cloud computing paradigm makes machine nodes interchangeable, thereby making it easy to add or remove nodes, and the resulting system is often quite fault-tolerant. This is thanks to the underlying networking technology, which presents the illusion of a fabric, where any two nodes in a cluster have reasonably uniform latency and throughput when they communicate. On the other extreme, the high-performance computing paradigm, or HPC, is most applicable to supercomputers with dedicated nodes and links. If one node or link goes down, it cannot be replaced with another node or link without impacting the cluster's performance. And this is due to the specific network topology, where each node has a fixed set of neighbors. If one node goes away, you plug in another node from somewhere else, it's not going to have the same performance characteristics. Such a system is usually less fault-tolerant, and it relies on restoring from the last checkpoint when a node or a link goes down. And this kind of restoration can take some time, and it can lose some system progress. An ML framework such as TensorFlow needs to make these two types of systems jive well, because the top half of the system is often deployed over a data center cluster following cloud computing, but the bottom half can be driving a TPU cluster, like with dedicated nodes and links following HPC. So some research here can be useful. For example, when an HPC cluster has a down node or link, can we continue to operate with degraded performance and try to minimize the impact? This has been some very interesting initial results, and we would love to follow up on that. Now, let's wrap up. In this talk, we covered some interesting problems and ideas in building ML infra and contrasted it with data infra. We hope this will help spark some interest in collaborating between the data and ML infra communities. Here are a few possible directions to explore. First, adding ML to data infra systems seems like a popular approach. I personally hope that such integration will focus on looking into some deep infra problems, like the push versus pull-based execution model we talked about, instead of just using a shallow integration approach, say running ML models as a black box through SQL's user-defined functions. Next, I would like to invite you to apply the database technology to building ML infra. Spark made a good example of applying query optimization to ETL pipelines. And finally, it might also be interesting research to try adding SQL support to ML infra like TensorFlow. A possible product benefit is to provide a single environment for users to play with their data and run the ML models. And a possible research benefit is to have a common code base as a collaboration vehicle between the data infra and ML infra researchers, so that they can play with ideas that might cross-pollinate and integrate. For example, how we apply NLP to SQL query. If you would like to explore collaboration, please follow up with me. There are a lot of interesting problems waiting to be solved. I want to end this talk by thanking Eric Johnson, our product manager of TensorFlow Runtime, for helping me put together this slide deck. I also want to thank my Google colleagues, Yuri Sitsa, Hakan Hasigumas, and Lydia Rowan for their insightful feedback and suggestions on the talk content. Thank you all, and look forward to following up.